Hello everyone, this is Dharani and we have Rohit and Rakesh with me, my fellow presenters today. So we are here to present our project on model to diagnose Parkinson's disease. We hope that you will all find this topic informative and interesting. Um, to start with the introduction, to have a background on Parkinson's disease. Parkinson's disease is a neurodegenerative disease that affects about 70 to 10 million people over the world. This disease is generally not detected at the earlier stages of a disease. Uh, by the time we uh, by the time we detect the disease, it is already too late to diagnose the patient with a Parkinson's disease. So to treat this disease, usually we need sensitive diagnostic tools to detect the Parkinson's disease. But as the advancement in the technology, we are collecting the audio samples of the patients with Parkinson's disease, and we apply reliable methods on those audio signals to translate into diagnostic tools for PD detection. So once we transform those audio signals to diagnostic tools for PD detection, it is very much more accurate and cheaper. So to validate this concept, we provide evidences by using audio data set collected from the people with and without Parkinson's disease. So in this project, finally, we explore the effectiveness of ensemble methods like bagging algorithm, which is a random forest classifier, and a decision tree algorithm, uh, which will we perform all this ensemble methods on the data set taken from the UCI machine learning repository and accurately diagnose individual with Parkinson's disease. And also we apply PCA on this data set so that we will finally conclude whether this PCA plays a good role on the data set or not. So coming to the outline, we initially perform data pre-processing on the data. Data pre-processing is very much important before building the model and the data set, which means a good pre-processed data is very much important than a powerful algorithm. To the point, machine learning algorithm with a bad trained data will lead to the harmful analysis, which will result to the bad prediction. So data pre-processing is very much important. Data pre-processing in our project involves data scaling, which where we normalize the data on the range of independent variables, and we perform data standardization. Then we perform data splitting. All those are performed on the data pre-processing. Once the data pre-processing is completed, we perform principal component analysis. Principal component analysis is a process where we reduce the dimensions of a data set by increasing the interpretability, and also we make sure there is no information loss as part of PCA. Then all these three classifiers are performed on the data set before PCA and as well as after PCA. Then after performing all these classifiers on the data set, we get both accuracy and precision. But we interpret the results based on the precision because I'll give an example. Like if a cat is called as a dog or a dog is called as a cat, there is no much impact on the results. But in the sectors like healthcare, in the healthcare sectors, if a person is not having a disease, and if we said that he is having a disease, there is no much there is no much impact on the result. But if a person is having a disease and said that he is not having a disease, it is said that there will be much more impact. So we take a precision values rather than the accuracy values to interpret the results. Then finally we conclude based on the results. Then coming to the workflow, we initially take the real life problem. In this case, the real life problem is that model to diagnose the Parkinson's disease. Then we come up with a plan to find the resolution for the real life problem. We take the raw data set and perform feature extraction, which includes PCA, which means we reduce the dimensions, we split the data. All those are performed under the feature extraction process. Then we perform the splitting of data, like we divide into to train and test data. Then we perform machine learning algorithms on the trained data like decision tree, random forest, and XGBoost algorithms on those trained data. Then we compare the results uh, for these three algorithms, and we predict which model is best for a data set. Then this is the overall flow of the project. Then coming to data set overview, as already said, we have taken this data set from UCI machine learning repositories. The data set consists of 755 rows and 755 columns. And the characteristic features are that it contains integer and real values, which means there are no categorical values. All the variables are continuous. Then we have 11 features overall, which includes baseline features, intensity parameters, format, frequencies, and etc. And the class variable is the target column. Baseline features, which means demographical or medical information related. Format frequencies, which includes in our data set, there are F1, F2, F3, and so on. Bandwidth parameters, which includes B1, B2, B3, and so on. These are the this is the overview of a data set that we are taking. Coming to exploratory data analysis, we perform EDA on this data set so that we analyze the data. We analyze the data by performing EDA, and we hypothesis the test, and we divide the patterns, and also uh, we come to the conclusion based on the graphical representation by performing EDA. So we have generated two graphs. From the first graph, we can see that there is a significant values in class 1 compared to the class 0, which means we found that the data is imbalanced. Even though the data is imbalanced, we are continuing with the imbalanced data rather than converting into a balanced data. Uh, if we find the models are overfitting or underfitting on imbalanced data, then we can make this data balanced and perform the models again. But for now, we are continuing the models to build on imbalanced data itself. Then when we create the class variables on gender, like male and female, we see the ratio between class 1 and 0 is higher in female compared to the males, which means the males who are having Parkinson's disease are more when compared to the males without Parkinson's disease. Similarly, in the females also it is the same. The females who are having Parkinson's disease are more when compared to the females without Parkinson's disease. So the ratio between class 0 and 1 is higher because there is no much difference between the class 0 and 1 variable in female. uh, we have analyzed these data by performing EDA on the data. So after EDA, we have principal component analysis. This will be taken over by Rohit.
So the main motto of this project is to perform principal component analysis on our dataset. So why do we perform principal component analysis? It's one of the dimensionality reduction technique used to reduce the number of dimensions. So by doing so, we can reduce the computational cost and we can ease the visualizations, and then we can remove the irrelevant features from the dataset. So what does a principal component analysis do? So how do we do that? Means like we are identifying primary components from the data set. So these primary components are built in such a way that they explain certain amount of variance of each data set. For suppose, consider there is a data set having 20 columns and we want to build 5 primary components from those 20 columns. These 5 primary components are going to explain the 100% variance of each data set, of each column of the data set. And how we are gonna implement is by first we'll calculate the covariance matrix, and from the covariance matrix we will compute the eigenvalues and eigenvectors, and then we will do the primary component selection. So the covariance matrix is calculated by using this formula, and we have implemented the same code in our code, and we can see that this is the covariance matrix generated for this. So the covariance matrix will give a covariance between the two features. These features will explain the covariance. Sorry, these values will explain the covariance between two features. For suppose, as we are having a data set with 755 columns, we're gonna get 755 values for each primary component. So then component one is gonna explain the for each covariance between the PC1 and the PC2. So using this covariance matrix, then we are gonna build the eigenvalues and eigenvectors. As you can see in our next slide, we are gonna these are our eigenvalues and eigenvectors calculated from our covariance matrix. So these eigenvalues and eigenvectors are used for calculating the variance of each principal component, which can be shown over here. The variance is calculated by using this formula, which is the eigenvalue divided by the total sum of the eigenvalues. As you can see, we are having 755 columns. We're going to get 755 variances, which are explaining each of the columns. The first variance is around 12%. That means that the total entire data's variance, 12% variance of the data is explained by the column one. And the 9%, the value 9 indicates that the second column is going to explain the 9% variance of the entire data. And so on. So by plotting these values in a graph, we can identify like how much variance is explained by which column. As you can see in the first graph, this is plotted between the principal component and the explained variance ratios. So as you can see, after like 100 columns, the variance level is almost zero. So by taking a value around 117, we can explain almost 90% variance of the data set. So the same thing is represented over here, like using the cumulative sum of the explained variance. So as you can see here, like the 90% variance can be explained around 100 to 150 columns. So we're going to take a value between 100 and 150, which is going to explain the 90% variance of the data set. So after this, so as we have got the number of columns we have to build the PCA, we will give them as input to the PCA model, and then we will decompromise the data set from 755 columns to 117 columns. And then we're going to proceed with applying models like the decision tree, random forest, and the XGBoost. Before that, we're going to do the PCA. Before that, we're going to do model building without implementing PCA. And here Rakesh will take on from here. Rakesh, you're on mute.
Sorry. Hi all. Let's see how our models perform without PCA. Let's take a look at decision tree. It's a supervised machine learning model. Like a tree, a decision tree also has branches, root nodes, child nodes, and so on. The branches several factors. It splits data into branches like it achieves like this till it achieves a threshold value. Let's see the accuracy scores of the decision tree. The accuracy score for decision tree is 0.85 and the precision score is 0.89. What is accuracy score and what is precision score? Accuracy refers to how close a measurement is to true or accepted value, whereas precision refers to how close measurements of the same item are to each other. Now let's take a look at random forest classifier. The accuracy score for random forest classifier is 0.8, whereas the precision score is 0.87. For XGBoost classifier, the accuracy score is 0.85 and the precision score is 0.87. Now let's see how these results look like after PCA. After PCA, the accuracy score for decision tree is 0.72 and for the precision score is 0.85. Now we are plotting ROC curve and precision recall curve to have a better idea of our results. What is ROC curve? ROC curve is a graph that shows the performance of a classification model at all the possible classification thresholds. It is plotted between true positive rate and false positive rate. Now, if you have a look at our ROC curve, it is as follows. And if we have a look at the precision recall curve, it is plotted between precision and recall. Now, if we have a look at random forest classifier after PCA, we are calculating random forest classifier for 500 trees. The accuracy score is 0.81 and the precision score is 0.81. And the ROC and precision recall curves are as follows. And if you have a look at XGBoost classifier, the accuracy score is 0.78 and the precision score is 0.85. And the following are the ROC curve and the precision recall curve. Now my friend Rohit will take over.
So as we can see over here, like we have the results from all the three models we have built, the decision tree, the random forest, and for the XGBoost. So out of all these models, we can see that XGBoost have performed the best of those models. This is because of the implementation of the boosting, the way the boosting model works. As if we compare a bagging model with a boosting model, the boosting model adds weights to the leaves, so that's why it performs better when compared to a bagging model and or a decision tree. As we can see over here, like we are having a result of around 86% precision for a boosting model, whereas it's around 81 or 82% precision for a random forest model. So we can conclude that the boosting model performs well when compared to the other two models. And if by implementing PCA, we are gonna have a trade-off in the precision and accuracy. If that is an acceptable trade-off, then using PCA would be the most suggestible method. Yeah, that's our conclusion from our side.
Thank you.
Thank you all.